Okay, let's start now. Good morning to everybody and welcome to the Instituto Astrofísica Andalucía seminars. Today it's a pleasure, and I have to say that I'm very proud as director of the Instituto and also as member of the EHT collaboration to introduce this seminar. As you know, last week, the Event Horizon Telescope showed the results about the first image of the black hole at the center of our galaxy, the Milky Way. And in this work, our institute, the Instituto de Astrofísica Andalucía, played a very relevant role. It is, in fact, a great pleasure for me to introduce José Gómez. José Gómez, besides a good friend and colleague, is the leader of the Event Horizon Telescope group here at the IAA. He's member of the Science Council of the collaboration and is also one of the leaders of the imaging working group of the collaboration. It means that his role is really very relevant within the whole team. José Luis is investigador científico here at the Instituto de Astrofísica Andalucía. His career is focused on the study of the relativistic jets of active galactic nuclei with the highest angular resolution, and in fact making use of the most important networks, interferometric networks in the world. I would like to mention especially his work on millimeter VLBI, making use of the global millimeter VLBI array, also with the VLBA, and especially also with radioastron, that is one of the antennas that it provides baselines, including also antennas in the space. But José Luis is not only making fantastic and incredible images with the highest angular resolution, he's also very well known and has a very well known reputation because of the interpretation of the results that he is getting along the years. In fact, I would say that he's combining the observations together with magnetohydrodynamic codes just for the interpretation of the results, combining them also with emission codes. Today, I am sure that we are going to enjoy one fantastic seminar in which incredible results, the results of the black hole at our galactic center, that together with the results that were already published 3 years ago of the black hole at the center of M87, have provided a fantastic view of the physics of black holes, yes, confirming what Einstein predicted more than 100 years ago. José Luis, it's a pleasure for me to give you the word.
Thank you very much. In fact, a pleasure.
Yeah, take it.
Okay, so thank you very much, Anton, for this beautiful introduction. Well, for me, it's really a pleasure to be here. 3 years ago, we were in this room and we were showing to you the first image of a black hole ever taken by humanity. That was on the Galactic Center, the black hole at the Galactic Center of the galaxy M87. And last week on Thursday, we presented the first image of the black hole in our Galactic Center. So for me, this is really a special occasion to share with all of you how we actually made that image and the long journey until we finally publish these results. This is going to be a special seminar because it's going to be given by the group at the not only one person, but the full group of the EHT collaboration here at the Instituto de Astrofísica Andalucía. And then we will have the presentations from Guang-Yao, Zhao, from Thalia, Traianou, from Ilje, and Antonio Fuentes, who is going to tell us how we actually made this possible. So let me then start with the animation that we showed during the presentation in ISO to show the first image of the black hole at the galactic center. So if we sit in the Atacama Desert in Chile, and if this works, which it doesn't seem to be working. Sorry, I cannot pass these slides. Something is wrong. Okay, no, perfect. All right, so this is an animation that shows that we are zooming into the galactic center, and of course, as you know, in the galactic center, we have a lot of dust and material that is obscuring the center, so we need to observe this in infrared, And this is a continuous zoom in from observations taken with optical and infrared telescopes. And when we get closer and closer to the center of our galaxy, then finally, for the first time, we have been able to see the giant Larkin at the center of our galaxy, the image of the actual black hole that we have in the galactic center. So it was really a pleasure to see that after all these years of hard work, we finally obtained the image. And it was, of course, scientifically very relevant, but it also captured the imagination of the general public. And here you can see on the left, this is a collection of the covers of the different newspapers around the world. And that was really a special occasion in April 10, where you can see that the image of the black hole made it to the cover of the most relevant journals, and also in the news, in TV and radio across the globe. And this is a collection of the similar collection of the covers, in this case for the image of the black hole and our galactic center. As you can see here, it was also very well covered by the press, and it also made headlines because, of course, this is the second image, but this is the black hole in our galactic center. It's our own black hole, and for the first time, we have the proof that it's a compact object that actually is a black hole, as we will see in a minute. So on May 12th, we published a special issue in the journal Astrofísica Journal Letters, and this is a screen capture of the presentation of this special issue, in which, as you can see, we published 6 papers associated with the first results of the EHT of the Galactic Center. There is a first paper with a summary, then one paper displaying the observations, multi-wavelength coverage, then our beloved paper 3, which actually shows the images. Then in paper 4, we do an analysis of the interferometric data to determine with a high accuracy what is the actual size of the ring. In paper 5, we give a theoretical interpretation comparing the observations with relativistic MHD simulations. And in paper 6, we comment on the relevance for our understanding of gravity and how this fits into general relativity. These 6 papers were also accompanied by 4 extra papers, and actually 3 of them are focused on the fact that Zhao A is a highly variable source. It changes in the time scales of minutes, as we will see in a minute. And this was actually what drove us completely crazy. So many people ask, why, M87 first, and then Zhao A, why took you years after you published M87 to publish the image of Zhao A star? And the reason was because it's highly variable, and then we have to develop completely new algorithms. And actually, as I said, we are publishing 2 big accompanying papers just to explain how we actually dealt with the variability. So as we always like to say, this is a big international effort. And in the case, we love to say that science is a collaborative thing, especially nowadays where we have this difficult international situations with a war in the 4 steps of Europe. But in the case of the EHT, this is basically a necessity because we have used telescopes spread around the world. So we do need to have this really huge collaboration. And it's also a great pleasure because you meet really fascinating people, completely different cultures, but with the same goal, the same enthusiasm and the same vision of making the first images, and as we will see in the future, later on, to make the first movies of black hole. So this is a big collaboration with more than 300 people. This is the last, that was the last collaboration meeting in Hilo that we had in person. But today, what I would like to stress is the relevance of the group at the Instituto de Astrofísica Andalucía in Granada, Spain. And this is the collection of pictures from the group. And just briefly to comment that we have Rocco Lico, who was one of the co-leads of the gain transfer from calibrator to Zhao A, which was really essential Guang-Yao Zhao, who is one of the coordinators of the image of the scattering working group in the collaboration. Thalia Traianou, who is a member of the Junior Science Council of the collaboration. It has been also very active in clean imaging. And Ilje, which is our imaging guru, he knows everything about imaging. He can do imaging with many different techniques. Of course, Antonio Verdi, who also participated in clean imaging, and our movie maker. This is Antonio Fuentes. We have, as you will see, he will show the first attempt to make movies out of Sgr A, and he is our expert about making movies of black holes. And the new acquisition, the new members of the team, Teresa Toscano, who is just recently joined the collaboration, and our future, promises, Rohan Dahale and Mariana Forsky. I'd like to stress that this was a very big effort, but I think we should be really proud of the work of the group at IAA. It's one of the most relevant groups in Europe, and I would say in the whole collaboration. And let me show you here just why, what was our main contribution to this paper. As you can see, this is a screenshot of paper 3. This is their paper. This is the paper with the image. This is what everybody was expecting. This is what everybody has seen. This is what drove us crazy to get this image. This is the first step. Then all the theoretical interpretation comes after this. But this is the image. This is the paper. This is paper 3. And we had a really very, very relevant contribution to this paper. As you can see here, there are, for each one of the papers that I mentioned before, we have coordinators for these papers in the collaboration. In paper 3, I was honored to be one of the coordinators, also as one of the imaging working group coordinators of the EHT, together with Katie Bowman, that you may remember. She made headlines when we showed the images of M87. She's one of the other coordinators of the paper in the imaging working group. She's now in Caltech. And the third coordinator is Kazuo Akiyama, who is in Massachusetts Institute of Technology. So we coordinated this paper, and our group at the Instituto of Astrofísica Andalucía had a really huge contribution on this. The images that you have seen, and if you go into the paper, you will notice that we have used 4 different imaging pipelines as described here. CLEAN, which is a classical method for interferometric imaging, EHT and the SMILE to RML method, and THEMIS. CLEAN was developed here. The algorithm was developed here and was run fully here. So 1/3 of all the images were run in the house and developed in the house, embedded in the house. EHT is the other powerful method. It was supervised by Katie, but all the parameter surveys, all the images, millions, and I'm talking about millions of images performed in Google supercomputer, Google Cloud, were performed by our movie maker and Antonio Fuentes. SMILE, we have 2 experts of SMILE here, Guang-Yao Zhao and Kotaro Moriyama. It was supervised by Kazu, but Guang-Yao is one of the coordinators of the SMILE working group. So he had also a very important contribution in the SMILE images. And then we have a 4 pipeline, the full variation method, THEMIS, which is, we did not touch this. This was fully developed by the Perimeter Institute in Canada. So as you can see here, the relevance of the image of the first black hole in our Relativity Center was basically, half of it made in the house, as happened also with M87. In M87, we used 3 of these pipelines, and we did the whole thing of CLEAN here in the house. Not only this, one important aspect was the calibration of the gains. This is very relevant, and for this we had to first image all the calibrators of Sgr A. And Rocco, who is joining us online, I'm sorry he couldn't be here today with us, and Rocco was actually the lead of the gain transfer from calibrator to Sgr A, which was really driving us crazy because variability was tangled with gains. So we need to get a very good constraint of the gains. Otherwise, we could not constrain the variability. And Rocco was one of these leaders. As you will see, scattering is very important. this is not affecting MT7, but the galactic center is right at the galactic center, and it's well known for more than 50 years that there is scattering, especially at long wavelengths, but it's also affecting 1.3 millimeter. And Guang-Yao is one of the coordinators of the scattering working group. So he did all the work here. Without this, we could not have had an image of the Sagittarius. Dynamical imaging, we have not made a lot of noise about the first attempts to make movies, but you will see our attempts. And this was completely done by Antonio Fuentes. You will go to paper 3. This is a full section, which is section 9. Antonio did all the analysis of dynamical imaging. And of course, we participated, as we mentioned, clean from the contribution from Ilje, from Thalia, and from Anton. So I'm sorry that it sounds a little bit like you are selling yourself too much, but I think we should be proud of this. And I want to share how proud I am of these people. These are our geniuses. These are the people that made this possible. And thanks to the support of the Instituto Astrofísica Andalucía, they have been able to make this significant contribution to Sgr A. Okay, so I think that was it. So and now we will have the presentation from the different people in the group to explain how we actually managed to get the image of the black hole. And the next speaker is Rocco. Rocco, are you online?
Yes, I'm here. Can you hear me?
Yes, please go ahead.
Okay, great. Thanks, Jose. So it's really a pleasure to be here today. Thank you all for being with us, for sharing these results. And let me say that I'm also extremely proud for being part of the IAA team. This is really the best thing I've ever done in my career so far. So thank you so much, really proud. So, and I'm sorry for not being there because of the COVID, I had to stay home. So let me go straight to the point and start with the story. For being able to take the image that José Luis just showed, we use the so-called very long baseline interferometric technique, which combines the signal from several telescopes spread around the globe and allowing us to simulate a telescope which is as big as the Earth. So what you see here, so what an interferometer measure is just a set of complex visibilities, which sample the Fourier components of an image. And in the middle panel, the so-called UV coverage, what you see here, this is just the projected distance across the several antennas called baselines as seen from the source. And as the Earth rotates, we feel more and more this plane, which is essential for then being able to reconstruct the image. And you will hear many more details about this from my colleagues during this talk. Next slide, please, Jose. All right, so in the specific case of Sagittarius A star, we observed the source with this array of 8 telescopes spread through the world. You see from Hawaii, Mexico, Arizona, Spain, Chile, and South Pole. And we observed at 1.3 millimeters in 2017 for 5 days in particular, April 5, 6, 7, 10, and 11. By taking into account several things, like the days where ALMA did not observe, ALMA is the most sensitive antenna of the array, and by taking into account that there was an X-ray flare during April 11, it turned out in the end that the day with the best data quality is April 7, which is also the day where the IRAM ferrometer station from Sierra Nevada observed. And this provides us with the best UV coverage, as you see in the right panel here to the bottom left. This is also the longest observation duration. This is the observation with the largest number of detection. And this is why we select this April 7 dataset as our primary dataset. And indeed, the image that Jose showed before, that was the image from this specific dataset from April 7. And then to the left, you see another UV coverage. This is from April 6, which is the second day with the best UV coverage. And we use this dataset as a secondary validation dataset. Next slide, please. All right, so this is brief animation to show how the whole process works. So we start with a bunch of telescopes spread around the globe, observing a source. Each one of these telescopes is equipped with an atomic clock and is sampling analog signals, which are then converted into digital signals. These data are then stored into our drives, and then they are shipped to the calibration centers where we have supercomputers doing the so-called correlation of the data. And then after this process, we have the a priori calibration, when we align the faces of all the different telescopes and we correct the amplitudes, and then through several algorithms, we will be able to reconstruct an actual image. This is how the whole process works. And just to give you an idea about the amount of data, we start from petabyte of data with the raw data from the telescope until we reach the very last step of the actual image, which is really a few kilobytes. This is just an amazing thing. Next slide, please, Jose. All right, for Sagittarius A star, as Jose mentioned, we needed really special care, mainly because of the variability on very short time scales. This is something that will be also discussed from my colleague in the next slides. And for this reason, to calibrate the telescopes through the so-called antenna gains, we had to use two calibration sources, which are J1924 and RAW 530, which are, if you go to the next slides, please, Jose, which are sources with a very simple structure, very bright. Here, I'm showing 3 millimeter GMV plus ALMA images of the two calibrators and not the actual EHT images, because these results are still under embargo and we are still working on that, but they are going to be published very soon. So stay tuned for that. And by using the sources whose structure is stable across the observation, and also the flux density is stable, we managed to characterize the time variable antenna gains, as you see in the right plot, with the two colors representing the two calibrators. And each frame here represents a single antenna, and each value is not a single value, but is the result, as it was mentioned earlier by Jose, of multiple images, because for each calibrator, we have multiple calibration pipelines, we have multiple imaging algorithms, and then we have multiple people making the images. So this is the outcome of a huge results that took several months. And in the end, with that, we were able to interpolate these final gains to the Sagittarius A star timestamps, and then we transfer this to Sagittarius A star. And at this point, we are able to disentangle the intrinsic variability of the source of Sagittarius A star from the fluctuations due to instrumentational effects. So next slide, please, Jose. And this is the very last slide of my talk here. So during the EHT observations, there also was a multi-wavelength campaign. And you see here, there were different facilities, both ground array and space satellites, space observatories. For instance, you see here from the list with the different colors, we have some East Asian VLBI network observations. These results actually were very recently published by Ilje, one of my colleagues. Please take a look at this paper, it's very nice results. And then we have other facilities like VLT, GMVA, as well as satellites, Swift, Chandra, and Nustar. Let me say that this was really essential, having these constraints on the multi-wavelength, light curves, and variability for getting constraints on theoretical model selection, as well as the physical interpretation. And you will see how this information were used in the next talk. I think this is my last slide. Thank you very much.
Thank you very much. Okay, now we go to the next speaker, which is Guang-Yao Zhao. He is going to talk about what's happening and all that beautiful stuff.
Yeah, thanks. Okay, here. Okay. Yeah. So as I mentioned, we've been asked a few times why it took so long. Isn't this source much closer than the previous black hole? And the apparent size is actually slightly larger. But shouldn't it be easier? But unfortunately, for imaging this particular source, we face two unique challenges. The first one comes from the fact that we are in the same galaxy. To see the galactic center, we need to look through the inner galactic disk. But there are many things on the way. As a matter of fact, at optical wavelengths, we cannot really see the galactic center because of the extinction. While at radio wavelengths, it is turbulent ionized plasma that will scatter and distort our images. And actually, the scattering along the line of sight towards the galactic center is particularly strong. Although currently we know that most of the scattering actually didn't happen in the central area, but rather somewhere halfway between the center and us. So, okay, how exactly this will affect our images? In the regime of strong scattering, there are two distinct effects on an image. The first one comes from diffraction, which arises from small-scale turbulences in the plasma. The time scale for this to smooth out is also quite short. So in a typical VRBI position, we see the smooth effect of the diffraction, which is similar as a blurring of the image. And this is rather stable over time, and it is well determined. But there is a secondary effect, which arises from larger scale turbulence, which will take more time to longer than the typical VRBI observation to smooth out, which is a refractive effect. These effects further distort the image. It's really similar as seeing through the hot gas following a jet. But so these effects compare in contrary to the previous one is rather stochastic. It's also difficult to handle. So, and how this affects our exact observing data. So if the source is not scattered, we will see the amplitude like shown here. Yeah, but the blurring kind of actually redistributes the flux in a slightly larger area, so it kind of drops down the amplitude and also the signal to noise ratio at the especially longer wavelengths. But on top of this, the refractive effects further modulates the data. Okay, because this change will also take longer time to average out. So at a single VRBI observation, we see a random realization of these refractive effects. So how exactly we can handle the data which is scattered? For the blurring, as is well determined, we can simply use a method which is called de-blur. But the tricky one is the refractive one, which is more stochastic. And it depends on the intrinsic source structure. It also depends on the actual magnetic field configuration in the scattering material. So what we did is we use the existing tools. We run lots of simulations using several up to 7 geometric models. We image many random realizations of the scattering and take the standard deviation of them to get the level of the refractive effects, and we treat it as noise so that we increase the error budget of the actual data. And after this, we would say the chi-squares we get will be more reasonable, like around 1 here. Okay, so another effect comes from the time variability, I think, as José and Rocco already mentioned. Compared with MET7, although the two black holes have quite comparable angular size, but in the actual linear scale, Sagittarius is more than like 1,500 times smaller. So although the material around near the event horizon moves at the speed of light, near the speed of light in each case, but for a black hole as large as MET7, it takes several days to make a full circle, while in Sagittarius, this happens in several minutes. And this breaks one of the basic assumptions for VLBI imaging. As Rocco mentioned, we need to wait when the Earth rotates to sample in the Fourier space. But if the source is changing, it feels like we have set up a long exposure to take a photo of a puppy, but it's keep chasing its tail in the same time. So how are we going to do this? Again, we try to characterize the variability. And apparently most of the largest contribution comes from the overall flux, the brightness change. And so since one of the two of the elements like ARMA and SMA have measured the total, the light curve quite well, so we can normalize the flux. After this, we take out the largest contribution of the variability, and the rest of them can be well described by a broken power law, as shown here, and on the right side plot. As a matter of fact, the variability actually exceeds the level of refracted noise by an order of magnitude. So, and again, we treat this as noise and add this as additional error budget to the data. So it is fine for the data to be imaged as a static source. And now Ilje is going to talk about how we actually build up the imaging pipeline and how we test and validate the results.
Yeah, thanks a lot, Guang-Yao. Yes, now I'm going to briefly introduce the basic process of the VABI imaging. So first, if we have the perfect telescope, which is the size of the Earth, then there's the imaging, just getting the image of this the small black hole would be much easier. But that is not realistic, since we have just a number of telescopes which is spread all over the world, and there are still a lot of holes between the telescopes. So that makes this kind of fundamental problem, which is so-called ill-post. So always the number of the pixels of the image we have to obtain is larger than the number of points of we have in the data. So it is difficult to get the unique solution from our observed data. Unless we have the enough number of the information. So for instance, if we observe this kind of cute puppy in the universe with kind of the similar observation with our VABI system, then there is still a possibility to get the similar images, which is still not a puppy or something like that. So we need to be really careful to analyze our observed data to get the correct image. So to convince ourselves and get the right image of the observed source, we first used different imaging softwares which approaches different ways. So the first one is so-called deconvolution method, and one of the representative the method is so-called clean, and this is based on the assumption of the image, which consists of a number of point sources, and this is most conventional way of the imaging of the VABI data. And we are now using the software named DiffMap, and especially all of our IAA members participated in the imaging and just the led of the development of the DiffMap pipeline together. And also there is another the way of the imaging, so-called regularized maximum likelihood, and this approach is a little different with deconvolution method. While the convolution method starts from the inverse Fourier transform, this regularized maximum likelihood starts from the visibility data, so-called forward modeling. So first we fit the model to the data and finds the best model which fits the data very well. So for this method, we are now using two representative softwares named Smiley and EHT imaging library, and from IAA, we also participated in these two imaging methods. Also, just Antonio and Guang-Yao led the part of the imaging pipeline development and also the coordination of the imaging. And another one is, as José introduced, there is full Bayesian approach, which is new for this Sagittarius imaging compared to the M87, which is mostly developed by the Parameter Institute. This is completely different with the other the methods as well. So we can independently make sure the results from this method as well, together with the other methods. And for this method, we used the software named Themis. So as Guang-Yao also introduced briefly, before going into our real data set, we first convinced ourselves of this imaging method and software together with the synthetic data. So first, we generated 7 different kinds of the geometric models, which has a different shape, like from the crescent, ring to double source or just point-like source. And then added the similar noise with the real Sagittarius data of the variability and the scattering. And then as a result, we have this kind of the synthetic movies actually, which resembles the real Sagittarius A star data. So for all these synthetic models, we did the imaging with different pipelines and different softwares, which consist of tens of millions of the parameter combinations. So based on this a lot of images, we selected the top set parameters, which is successfully reconstruct all these images across all different imaging softwares. This shows the results of the reconstructed images for different geometric models. And as you can see, even with this same imaging parameter for each imaging software, that reconstructs all different shape of the geometric models. So based on these top set parameters, we applied the same parameter set to the Sgr A simulation, which more resemble the real Sagittarius A star data. And then these are showing the result of the images of this Sgr A simulation, which also quite similar with the ground truth image. So after convince ourselves with this kind of full process, we move on to the Sagittarius A star data. So now Antonio Fuentes will introduce our real Sagittarius star data result.
Okay, thank you, Ilje. Okay, so now that we have trained our algorithms and the pipelines are ready for imaging Sgr star, let's see what we got. So all these images, all these thousands of images that you see flying around here are possible appearances of Sgr star. So while all these images are slightly different, all of them are consistent with the data and can represent the true source structure. So if we average all these images to emphasize the common features, what we obtain is a bright ring with a central dark region. But if we take a deeper look at these thousands of images, we can see that we can further cluster them into 4 different categories. So the vast majority of these images can be classified into these 3 first clusters that show ring-like structures. But also there is another cluster which is really very much smaller in comparison with these 3 that also contain images that doesn't look like ring-like structures. But when we look at the average image of all these 1,000 images, what we see is this bright ring of plasma that is surrounding this central dark area, which has a diameter of exactly the same size as what was expected from previous observations and theory. So now you might be wondering, why do we have 4 different clusters of images for Sgr star and just one day, when for M87 we have this just a single image for each day? So this is because of 2 main reasons. First is because of the sparseness of the IAA-EHT array, which was introduced by my colleagues, and also because of the intrinsic source variability, which was also introduced by them. So to get some intuition on what it's like to get to capture a picture of Sgr star, so let me play another movie. Okay, so here we have placed a camera on the Dolomite Mountains in Italy, and we are recording the scene during 12 hours, just as our observations. So if instead of this recording, what we take is our snapshots of this movie that we are seeing here, what we will see is that we can also classify this snapshot based on their appearance into 4 different clusters, just as we did with Sgr star. So now we are forming these clusters based on the different type of clouds, weather, and so on. This is just an analogy of what would be like to image to Sgr star, but it's not actually the same. Actually, Sgr star will be the mountain will be moving itself as well as the clouds surrounding it. So we can get these 4 different cluster of images, but we can also get the average image of the Dolomite Mountains during these 12 hours observations. But what if we try not only to get an average image of Sgr star, but also reconstruct the dynamics that we know that they are present in the black hole. So we tried that. We did a first attempt of movie reconstruction of Sgr. We got some results. I will show you this now. But let me first introduce a few concepts. So as my colleague said, the EHT coverage is sparse, which makes reconstructing an image a difficult task. But if we, instead of just taking the full length of the observation, we just take chunks of data of 1 to 2 minutes length, then the EHT coverage is even more sparse. And reconstructing a reasonable image is just not possible. So in order to overcome this issue, we developed methods that impose strong priors on the source structure and can actually reconstruct movies of this very little information. We also focus on a time window of a bit less than 2 hours, because this time window is the one during the whole length of the observation that contains the best coverage and that allow us to reconstruct the dynamics of the source. But first, let's test our methods with GRMHT simulations of Sgr to see if we are able to actually reconstruct the dynamics of a source for which we know what are the dynamics. So here we have on the top row 2 GRMHT simulations which try to resemble Sgr, which are also affected by scattering, as you see here. And these are the movie reconstruction that we got for these 2 simulations. And here on the right, what I'm showing is a figure that we have used a lot in the paper to quantify our ability to track the true dynamics of the simulation. So what we see here, these are 3 snapshots of the simulation, and here we see in red what we see here is the position angle of the ring as a function of time. And here in red, we have this curve in red is the true position angle of the ring during this time window. And then in green and blue, we are seeing the densities of the histograms of the reconstructed movies with our methods. And we see how we are able, within some uncertainty, to actually reconstruct for this particular case, the true dynamics of the simulation. So now that we see that we know that we can reconstruct the dynamics of sources for which we know the true dynamics, let's see what we got for Sgr. Okay, so yeah, here I'm showing the results for Sagittarius A*. So we have here 2 panels for April 6 and 2 panels for April 7. So these 2 movies were made using something we call a different level of temporal regularization, which is the amount of continuity that we allow from frame to frame when we do a movie reconstruction. So for April 6, if we allow less continuity from frame to frame, and if we also allow more continuity from frame to frame, we see that we obtain mostly the same, basically the same movie, which is just as a movie which is mostly static, and we have with a ring which is brighter in the upper right side. On the contrary, on April 7, when we allow less continuity from frame to frame, we obtain this interesting evolution during this time window in which these bright components move from this side to this side. But if we don't allow that much flexibility, then what we get is this mostly static movie. So with this very little information that we have in the 2017 observation, we cannot actually constrain for April 7 which one of these movies is better than the other and which one represents the actual dynamics of the source. So our results are not conclusive, but this first attempt set the path forward to get the first actual movies of black holes for the next observations of Sgr. We also perform geometric modeling of Sagittarius A* directly on the interferometric visibility measured by the array. So with this geometric modeling, what we found is that a ring is the best geometric model that best fits the data. And with this ring, we can extract some properties and then get an estimation of the diameter and so on. So using these ring models that you see here, which are characterized by the width, diameter, and position angle, what we obtain for Sagittarius A star is that the ring has a diameter of 52 microsecond, a thickness of 30 to 50% of this diameter, a gravitational radius which is around 5 microsecond, and a black hole mass which is around 4 million times the mass of the sun. Yeah, so I think that's from my side. So now Thalia will tell us about what we learned from the black hole.
So, in order to interpret the image of the black hole that we observed with EHT, we performed GRMHD simulations of the plasma surrounding the black hole. So we assumed of a torus of ideal plasma swirling around the black hole that has some ideal properties. Sorry. Yes. And we tried to set a to test specific parameters of how the system should look like in order to create the image that we obtain. So we checked the inclination of the spin of the black hole. We tested, we explored the existence of spin, and if the material around the black hole is swirling together with in the same direction with the spin of the black hole, or in opposite, retrograde or prograde, or the type of the type of the accretion flow. For instance, if it will have a magnetically arrested disk where the magnetic fields are ordered and dominates the accretion flow, or normal accretion, type of accretion where the magnetic fields are scattered and not interrupt the flow. So we evaluate these models based on the size of the image, the shape of the image. We simulated different spectra in a different wavelengths and the low frequency size of other images. So out of 1.8 million images that we created, we applying all these different constraints and criteria, we ended up with only two models surviving on all this process. Here we can see the best bet model that we obtained, and it's closer to the image that the Sagittarius A star image. So in these beautiful pie charts, we see a summary of what we have done in exploring the theoretical and the plasma flow around the black hole. So we see here that how which spin values we obtained, and the type of accretion, the temperature of the electrons present. With red color, we designate the models that fail in all the constraints that we set, and with green is the models that passed our criteria. So we have two models, as I mentioned, which corresponds to a magnetically arrested type of accretion. The material around the black hole is moving in the same direction with the spin of the black hole, and the black hole is actually spinning. And the inclination of the spin axis is around 30 degrees with our line of sight, and we have here the ratio of the electron temperature. So in summary, we created 1.8 million images, 1.3 million SEDs, that all corresponds to 50 terabytes of data. But besides the properties of the plasma around the black hole, we have also theoretical, we can test theories, different theories of, for instance, gravity and general relativity. Since Einstein published the theory of general relativity, we try to test it and prove that it's not valid. So for this, we have developed different tests in different regimes, gravitational regimes in our solar system, in cosmological level, etc. But EHT offer us to test these theories in a very strong gravitational field, very close to the horizon of a black hole. So it's particularly important the significance of these two images that we have obtained with EHT, because we can direct test and rule out many of these theories. So in this beautiful plot, we can see how well the Sagittarius A star and M87 follow the predictions of general relativity. So for these images, we saw that GR still holds strong, and especially because we know that with very good accuracy, the mass of the Sagittarius A star, which was one of them, was the Nobel awarded about this estimation. Because we know so well the mass of the Sagittarius A star black hole and the distance, we can predict with very good, we can test with very high accuracy the predictions of general relativity. For M87 with less accuracy, and here we can see also the predictions about the gravitational wave event that detected some years ago. So the beauty in this plot is that one of the predictions of general relativity is that black holes, despite their different environments or different sizes, can be described with just 3 parameters: their mass, their spin, and their charge. So here we can see black holes that differs in 8 orders of magnitude that can be described by the non-hair theorem, and this is really beautiful. We can see that still this theory works. And besides these predictions, we can learn a lot from the size of the ring. Here in this movie, we can see how well how the general relativity predicts the size of the black hole shadow, and if it's another alternative theory is valid, how much deviates. And here is the actual image that we captured, and we see the predicted shadow with a ring, with a green ring, and the actual measurement, which is with a blue ring. Also, we tested some other theoretical parameters, as assuming that Sagittarius A star was a reflecting surface with albedo 1, and or some other albedos, and we found that an object with a reflecting surface with albedo 0.3, it's only marginally different than the real image that we obtained. And to conclude, today we are able not just to imagine black holes, but to actually take pictures of them, and not only one, and several of them, and compare them. And here we can see how the size of these 2 black holes and how different is each other. M87 is 1,500 times larger than Sagittarius A star, and we can see how much exotic and difficult to imagine is these differences. However, we can compare, test, and measure their properties and conclude that can be described with the same way. And now, thank you. And now José is gonna tell us about more about the future.
Thank you very much, Thalia. Okay, so we are running out of time, but I really want to tell you what's next. Okay, so we have two black holes. So people say, hey, no, you know, this was actually the main goal for the EHT to image these two black holes. So we are going for what is next. So this is just the beginning. We are running out of time, but I really want to show you just a few slides to tell you what is expecting for us. So first of all, this is we are already working the next generation of the EHT. Okay, so this is a very active project, and this is a project which is actually funded by the NSF. We already have 12 million for the design. It's going to be 10 more dishes. This is the timeline. We do expect that in a couple of years we'll have the final review and start building in 2025, 2026. Okay, so this is really ongoing. So we are just getting started. So this is a near and black hole imaging. We have already made the science working groups with fundamental physics, black hole evolution, and also even transients and so on. So this is a really ongoing effort internationally across the globe. And we are having here also a very significant participation, leading one of the working groups together with Priya Natarajan from Princeton, and Thalia is also helping a lot in this aspect. And we want to put many different telescopes, and these are possible sizes. And you will see here, this is CNI. This is not the Centro Nacional de Inteligencia, but this is the Canary Islands, as the Americans think about it. And we are really trying to put a telescope in the Canary Islands. So we are discussing this with the presidency of the CSIC, and we have discussed this with the Instituto de Astrofísica de Canarias, and we are working very hard to try to get one antenna here, because we know, and we have already put a radiometer in the Canary Islands, in the Thalia Observatory, and this is a good site. This is actually one of the best sites that we are considering for the NGHT. So this is going to happen. We are going to have a telescope here. I don't know where we are going to get the money from, hopefully from Spain, but otherwise the Americans are going to put the antenna there. So we are really pushing forward to having one of these antennas, which is, leading from Spain and leading from the Instituto de Astrofísica de Andalucía. And as I said, this is almost certainly happening. Okay, so the antenna, as I said, has been identified as one of the best sites for covering Sagittarius A star and also M87. So it really provides excellent information. We are working very hard on this, and these are the main goals that we have for the NGHT. So you can see here the coverage and what we may expect with the NGHT. So we do want to make movies of M87, Sagittarius A, and test gravity. We will very soon, relatively soon in the next year, show you the first movies of how black holes accrete. So we are going to learn how we can extract energy from these black holes. We are going to make movies also of Sagittarius A. We are going to see a plasma moving around Sagittarius A. You saw from Antonio the first movies. With 2022 data, we may be able to get the actual first ones. And then with EHT, we will get explicit movies, and we will see material around, not just astrometry as we will see it. We will measure the spin of the black hole in the galactic center. So this is, as I said, just the beginning. And of course, we want to test GR. This is the most important thing. The image that we see here is a combination of different astrophysics, which is what we call N0, and then different rings, N1 and 2, these are the rings coming from the photons going around 1, 2, 3 times the black hole. These are the metric, so they actually prove the metric. This will be the first time we will actually be able to, with very high precision, tell at which point GR may break down. And this is one of the main goals of the NG-EHT, and this is going to happen as I'm going to show you here. this is what we expect to get with the NG-EHT with two different frequencies. So we will see the beautiful M2 ring. This is where all GR is captured. And we are leading this. The Instituto de Astrofísica Andalucía is hosting the first meeting of the EHT and NG-EHT collaborations in a month from now. So IAA is going to be in the center of black hole studies in the world. And as I said, we are taking a very important leading role here. And this is just a slide to summarize it, but I'm not going to read it, but I hope that after all this talk, we have convinced you that the amazing people we have here, these are the heroes, and they are really contributing significantly, and we are positioned in having a very strong contribution in the next decade. And just to finalize, this is what I usually like to show. Everybody here has seen the Interstellar movie, so this is science fiction. And now with EHT, science fiction has actually become a science fact. So stay tuned, and thank you very much for your attention.
So now the talk is open for questions. For doing the question here in the room, we need to move the micro. So from one to there, I need maybe the help of one of you to move the micro from the question to the answer.
Sure.
And I will manage. The question at Zoom.
Okay.
Just approach the micro to the person that.
Isabel.
Great team. I'm really proud and congratulations. I already said so, but I think it's, I think I'm sure that I can say that we all at the IAA share the proudness of being part of this and having you as colleagues. So that's a great challenge and you've done it. So congratulations.
Thank you.
And I'd like to make the comment that I think that we are all at the IAA, we are all proud of that. And we should not forget that it is also true thanks to something we have, would make us special as well, which is the Zgr A program. And two of the amazing people in your team are funded by our Zgr A program, from which we are all very proud as well, I'm sure. So thanks so much for giving us the opportunity of knowing how the black hole of our own galaxy was 27,000 years ago. That's great. Congratulations.
Thank you very much, Isabel. Thank you very much, Isabel. Of course, yes. And as I mentioned at the beginning of my talk, we do appreciate the support from the IAA as well as, of course, other funding agencies. But this is what really makes us proud to carry the name of the IAA everywhere. And you have seen this in the past days, how the IAA was, spelled out very clearly all around the world. So it's for us really a big pleasure.
Just to add that since you weren't here when you in Munich and the remaining team in Madrid, we shared the very special day here. We were many of us, and we even clapped, even knowing that nobody was listening to us on the other side. So we already had that. I mean, that's great feeling of someone sharing that incredible news.
Yeah, thank you very much, Isabel.
Yeah, the next Rainer, please.
Yes, Rainer.
Yes, hi. Well, first of all, congratulations to all of you. I mean, this has been said many times, but fantastic work and great presentations. There's two things that that I'm curious about. So two brief questions. The first one is when you do these, when you categorize, when you classify the possible solutions into 4 different images, 3 of them are really extremely similar, while one of them is quite different. Is there any correlation between the different imaging algorithms, or do the 4 different imaging algorithms all produce the same statistical distribution of these 4 categories? That's question number 1. And question number 2, I'll say it directly because that may be also related, I'm not sure. So during Antonio's talk, I was surprised that when you look at the April 6th and April 7 movies or average images, I think that is the same in this case, the bright spot is on exactly opposing sides of Sag A star, which is something that is surprising, giving both basically the face-on orientation. And do you observe anything like this in the in the simulations? That would be a question to Thalia, maybe. Thanks.
Thanks a lot. These are really great questions. I'm going to answer the first one, and Antonio, and then perhaps Thalia. So indeed, right now, one of the main things that, and this is why it took us so much time, was whether, when we get these not so ring-like images, whether they are produced by a particular pipeline or a particular set of parameters, or a particular prescription of variability, a particular prescription of scattering, or even the gains. I mean, so everything was playing around, and it was really crazy. And indeed, what we found is that this is not associated with any particular pipeline. It's not associated with any particular prescription. It's just a combination of the variability and the UV and the sparse UV coverage. So it's not something that we could have identified. Otherwise, we may have identified this, and then so we would say, okay, we can rule out these non-ring images. So we did work for literally for years, right now, to try to get an answer to that question. And let me pass it on now to Antonio for the movies.
Thank you, Rainer. So yeah, it's actually, yeah, it's true what you say. So for April 6, we have the bright spot on one side, and for April 7, we have on the other. Even if we don't see any evolution during the time window. And that's actually surprising, but it's something that we should be also careful when we interpret these results, because as I said, with little information that we have during this time window, which is actually the best region of the whole observation where we can attempt to reconstruct the dynamics, but still it's a bit of too little information to actually constrain whether this change in the orientation of the position angle is true, because also we have seen that when we change some of the parameters that we use in the dynamic imaging methods, we don't always get the same position angle. So this is very interesting, of course, including the evolution that we see in some of the movies on April 7th, but still let's be careful with the interpretation and wait until the next observation, where we will have more telescopes added to the array, and we will be able to constrain more the dynamics of Sagittarius A star.
Great. Thank you very much. Thanks a lot. And I do not want to be overcritical or anything. I mean, this is fantastic work. I just was curious. Okay, thanks.
Could you please repeat the question about the simulations?
Yeah, I think Thalia, yeah, the question was whether we do see something like that in the simulation. So,
actually, the brightness that we see in the simulations, again, we should be careful. Yes. And what we see about the brightness in the simulations, we should be careful, because it is based on many assumptions and has not some a direct impact in the image. So we tested some fundamental properties and not the actual where the bright patches should be.
If I may comment, just a final comment. Actually, Raina, yesterday, yes, I got an email from Nature, and one of the writers that they are writing an article about the results here, and they were asking me, so it seems that in your simulation, the material is rotating counterclockwise, while VLTI showed that it seems to be rotating clockwise. So is this in this agreement? So are you getting this disagreement with VLTI? And the answer is no, because actually we don't see it yet inside J star, which is what allow us in M87 to constrain the spin. So we don't know what may be the spin, whether pointing towards us or away from us inside J. So all we can say is that it's most probably rotating very fast, and it has a prograde accretion disk, but we cannot constrain with the data we had from 2017 whether it's rotating clockwise or anti-clockwise. And this is why what Thalia was mentioning. So we cannot say whether it's one side or the other, the one which should be brighter due to the Doppler boosting. So I hope this answers your question, Ryan.
Yes, I think so, roughly. Well, we can discuss about that. Anyway, I mean, there's nothing major in mind. It's just some curious comments that I have. Thanks.
Thanks a lot.
Is a question here? There is a question.
Congratulations for this spectacular institute. My question. I wonder if you can determine the mass acquisition rate for the black hole, and also it is also linked to the ejection. I don't know if this can happen in a black hole. I try to associate it because planetary physics to have both acquisition and ejection.
That's indeed an excellent question. Yes, with the comparison with the GRMAG simulations, we have constrained the accretion rate, which is very small as we expected. It's really we like to comment about an analogy. I mean, if we translate the mass of Sgr A to a person, so we can ask how much a person would eat. And the answer is that the person would eat 1 grain of rice every 1 million years. So this is a accretion rate of Sgr A. So it's really completely quiet and quiescent. Of course, completely different environments than M87, which is high accretion rate and huge luminosity, and this is why we see this amazing jet that we see in M87, and we don't see it in Sgr A.
There is a question online, Miguel Pérez-Torres.
Yeah, thanks a lot. Congratulations for the results and for the fantastic work, guys. Yeah. I also have a curiosity. Actually, I think it's a very similar question to one of those made by Rainer, and it's that because of this strong variability of the source, you said that within minutes the source is changing. You couldn't do the same, you couldn't obtain the same result as for M87. That's the reason it took so long. But still, when I see the image and I see these 3 bright spots, it would appear that there is something there. So, because if it is just variable within minutes, why shouldn't be basically smooth? All the just a ring with an average profile of similar flux density. So is this still? Do you think is an artifact, or this will be solved? Is this maybe something real here in those 3 bright spots? That's the first question. And then the second question I have is, is there any limit to the technique, in the sense that because you have the spin of the axis of the black hole, maybe if it is not let's say well oriented, you wouldn't have measured, in the case we have a jet or something that may hint to the spin. Is there any limit in the applicability of this technique to measure other black holes, supermassive black holes? Thanks a lot.
Hello, Miguel. Okay, let me answer the first question, and then I may have to ask you to rephrase a little bit the second, because I couldn't hear you very well. Okay, so for the first one, yes, we do see these 3 main dots you are seeing now in the image, but we think this is mainly also related to the UV coverage. We don't think these are real artifacts, and in fact, in with slightly different parameters, and we see a slight change in the brightness distribution around the ring. So we cannot provide the same constraints on the brightness distribution around the ring as we did for M87. So we should just consider that the most relevant here is that all of these images, and this is really amazing, all of them, even though they have different distribution of the emission around the ring, all of them have 52 microseconds. And this is exactly what it was expected from 4 million mass black hole. So we had the Nobel Prize, it should be 4 million, and now we say, which was, for saying that there was a very compact object with 4 million solar masses, and the image showed that this is a black hole. And this is the most relevant part. Whether the emission is bright in one side or the other, we cannot tell with this observation. We do expect to be able to tell this, and actually, We do expect to get the movies of Sagittarius A with hopefully with 2022 data, which was really excellent, and 3 more antennas, and of course with the future Ng-EHT. And then the second question, can you repeat it? Sorry, there was some noise here and I couldn't hear it.
Okay, so actually, well, also to clarify, I mean, that's fantastic. I also understood that these 52 microseconds do not depend on this, but it was my understanding that also the position and how this bright stuff is distributed carries a lot of very useful information. So that was my question, not a criticism, but actually, I understand this may not be real after all, or UV coverage and things will be improved. But that, I mean, please do not take this as a criticism. It's just that maybe there was something here that you can already say and not. But okay, that you answered this question. So the other one is, I mean, maybe I'm saying something stupid, but is that okay because you have the spin of the black hole that maybe you don't know about, maybe a priori. And here in this case, because there is no obvious jet from the source, if you have other supermassive black holes where the situation is similar, to which extent you are limited, or maybe not, by this technique, in the sense that maybe you need to have this face on or somehow, some kind of orientation. Is it relevant, the orientation of the spin axis of the supermassive black hole or not, to actually continue, doing kind of statistics of these measurements for other supermassive black holes?
Yeah, that's an excellent question, Miguel. Of course, I mean, the spin of the black hole will change the circularity and the size of the ring. So if we are able to measure, especially the N1 and N2 rings, we should be able to really determine what is the spin of the black hole. There is some degeneracy in the sense also if you see the black hole completely, from face on, then the spin actually does not change that matter the shape. But if it is edge on, you will see about 5% change in the circularity and the size of the ring associated with the spin. So this is actually one of the main goals that we would like to study with the next generation EHT. We do want to measure the shape of the N1 ring, and from there to get a very accurate estimation of the spin, which carry us a lot of information. Though, we want to study, one of the working groups of the one I'm co-chairing with Priya is to study the evolution of black holes in the universe, and in order to check how these black holes merges. Having the information of the spin is essential because the spin carries the information of the previous mergers. So this is especially interesting to, science aspect for ourselves.
Okay, thanks a lot, and congratulations again to the whole team. Great job. Carry on.
Hello, Miguel. We wish you were here to share this with you. Oops.
Curiosity with respect to the future, to respect do you have any other explanation than general relativity that you expect to be able to disentangle when you will have the new data with the new, or just you will confirm things, or are you, do you have any other alternative that you can test?
Yes, and actually the full paper 6 is on that. I think yeah, it's a beautiful paper, and of course there are many black hole mimickers. So they are boson stars and naked singularities and other solutions or deviation from GR, and this is exactly what we want to test. What we are measuring now here is that the N0 ring, which carries information about the size of the black hole, but we need to observe also N1 ring to get at what is the actual shape of the event horizon, which holds information of whether actually GR is right, or there are some deviation from GR. This is where, this is the strongest regime for GR. In the strong field regime, there is nothing stronger than that we can observe. So if GR breaks down, it's going to be there. And this is what we really want to measure. For instance, one of the most beautiful things that I saw that we have in paper form, this is Ramesh and Narayan from CFA who wrote that section, is whether there is a surface on this black hole. There are some mimickers And I don't know if Carlos is here, Carlos Barceló. We have had some beautiful chats about this. So one of the possibilities is actually LIGO people were looking for echoes from the gravitational waves. So if you have an object which mimics a black hole, it has a surface, you may expect some echoes of the gravitational waves. So in our case, we could see some reflection of the emission. And it's a beautiful analysis that shows that it has a surface, it has to be a complete black body, even though you have all the redshift, the gravitational redshift, but at the end it has to be a black body. And then we have been able to rule out with our observations that it does not have a high albedo if it has a reflecting surface, because otherwise the dimmer part of the ring, the central part, would be significantly brighter than what we have measured. So we are already, ruling out some alternatives to a curve metric from GR. And of course, this is one of the most relevant things we want to study with the EHT and NGHT. We have a full working group with the most renowned black hole physicists in the world, which are actually just working on that. And of course, for us, this is the most relevant. So yeah, understanding how jets are formed, understanding how we can start energy from black holes is very interesting. But checking whether at some point GR breaks down, of course, this is the ultimate goal of this. And this is just the beginning. So what I also like to say is that think about this for a second. You have two black holes here. We have shown we can image them. And this black hole has been there for hundreds of millions of thousands of millions of years. They're going to be there in the next few hundred million years. So imagine what kind of instruments we will have on Earth for serving these laboratories who are going to be there just for us. So imagine 100 years from now, what kind of instrument, what kind of telescope we will have. So these are the guys who are going to tell us whether, GR holds or not. And so it's really, this, as I say, it's just the beginning. I mean, it's only the beginning.
We just need to be there.
Yeah, we only need to survive for 100 years.
I mean, as a species. It's something questionable.
Yeah, that's also true. Yeah,
yes.
yeah.
There is a question online. Gerardo Garcia Moreno, please.
Hi, thank you very much for the presentation and congratulations for such an amazing result. I got two questions, one for Antonio and one for Thalia. First, regarding the process of constructing the image, you have like several images and you need to average among them to get the final image, right? So could you explain if you weight all the images the same, if you discard some of them when you perform this averaging?
Well, first, you can hear me, right?
Yes.
Yeah. Okay. So as Ilje mentioned, we first trained the algorithms with synthetic data, and then we made millions of images of this synthetic data, and then we discarded all the parameter combinations that were not passing a certain threshold regarding the quality of the reconstructed images. Since we knew what the images, the image reconstruction should look like, we could just discard those that were not good enough, and then we created these top set parameters that were able to reconstruct each one of these synthetic data sets independently and accurately enough that if able to reconstruct a ring, if it is a ring, or whether these parameters are able to reconstruct a point source, if it is a point source and not making a ring out of a point source or something like that. And with these top set parameter combinations, which are thousands of them for each imaging pipelines, then we image Sagittarius A star, and this is kind of the weighting that we applied for the averaging, these combinations that pass this threshold for this image that you see on the screen. So this is just the average of all these images that pass the threshold. Let's say.
So it's a uniform
with the same weight.
Okay, so it's a uniform averaging for the ones that pass these tests that you are doing. Okay.
Yes.
Thank you. And the other question was regarding this comparison with the magnetohydrodynamics of the plasma surrounding the black hole. First of all, the codes for such simulations require some initial conditions that I'm curious how you impose those initial conditions for the plasma surrounding the black hole.
Well, for the plasma, we assumed just an ideal plasma. We put some constraints for that, and then we left some free parameters like the spin, the inclination, and all the electron, of course, electron temperature, and so on. And then we test these constraints how affects the appearance of the black hole, and then we compared this. It was the second slide that I saw, the second movie. We compared what we obtained of these constraints with what actually see in the image. For instance, the shape, the size, and also we compared with ICDs that we simulated, and the low frequency appearance image.
Okay. And what kind of physics do this code include? Like, does include any kind of exotic physics related to the motion of the plasma, or is just standard magnetohydrodynamics in this curved spacetime?
No, it's a standard geometry.
And also replacing for computing the emission.
Yes, yes. And actually worth to mention here that with these simulations, we used 5 different geometry codes in order to be as accurate as possible.
Could you say it again? Sorry, I didn't catch it.
I said that worth to mention that for these simulations that we saw earlier, we used 5 different geometry codes in order to be on the safe side that what we obtain is reliable.
Okay, thank you very much, and again, congratulations for such an amazing result.
Thank you.
We have the last question. You don't? Please go on.
Hello, can you hear me? Hello? Hello, can you hear me? Okay. Congratulations for such a fantastic work and this result. But sorry for I just listened for half the talk, so I just have 2 basic simple questions. The first question is, I saw the image for the black hole, and I'm wondering which is a galaxy disk plane directions, and which direction is a black hole rotation directions. This is the first question. And the second question is, why there have 3 bright points around the black hole looks symmetric distribute, not like the first image from the M87. That one is half dark and half bright, because I think we are on the galaxy disk, and we just see on the rotation. So I don't know why the 3 bright part is a symmetric distribute. So that's the 2 questions.
The information that we obtain for the simulation is around less than 50, around 70.
Sorry, I can't hear you. Sorry.
There's a buffering.
Yeah. The other question of me was so you were asking about these 3 dots that you see in the image. So as we discussing before, you should not pay attention to the brand distribution around the image, but this is not well constrained with the variability of Sgr A. So and as we were discussing before, regarding the first question, the second that I wanted to find it's very interesting, because we see that the orientation of the black hole is not edge-on. So the spin of the black hole is not perpendicular to the galactic phase. So there should have been some different evolution of the inner part of the galaxy and the rest of the galaxy. So we are seeing this, like, from 30 degrees, which actually is in very good agreement with what the LTI observed. So they did some astrometric observation, and they seem to have followed the polarization of a spot around Sgr A. and the ones, you know, with a similar, you know, almost as seen phase on. So I think this is going to be also a very interesting piece of information that we should be investigating in the future.
Okay, thank you.
Last question, and the other is also related with data and so on. Okay, thank you very much to all the person, to all the team, to present here and also at Zoom. And good luck. Thank you very much.
Bye-bye, thank you.
Bye, thanks a lot.